Right, so hello, thank you everyone for inviting me to give this talk. Like Leo said, I'm gonna try to summarize briefly the state of the art of the AEN Torus. And the work that I'm gonna present is mainly based on the, but not only, on the GATOS collaboration led by Almudena Alonso Herrera. So since not all the audience are working on AGN, let me remind that AGN are no longer understood as a particular type of galaxy comprising 10% of the galaxy in the local universe roughly, but instead they are now understood as a short phase that can be as short as 0.1 mega years, which is nothing in comparison with other galaxy processes, like for example mergers, which take giga years. And in fact, not only one, but several AGN episodes might take place in a galaxy, depending on whether there is a gas supply to trigger and feed the supermassive black hole. So it might well be the case that every massive galaxy, which contain supermassive black holes in their center, might go through one or more of these AGN phases. And this phase has been proved to be very relevant for galaxy evolution. So now we have plenty of observational evidence for the impact of AGN feedback, which is the effect that the AGN has on the host galaxy, on very different scales, going right from the central parsecs of AGN, which is what I'm going to be concentrating on today, but also up to completely different scales of up to megaparsecs. Like for example, in this recent paper by Ignacio Martín Navarro, in which they see that the supermassive black hole in the center of the central galaxy, in a given galaxy halo, it's having an impact on the star formation histories of satellite galaxies, which, like I said, they are located at megaparsec distances from the supermassive black hole. So this is why the popularity of AGN has increased tremendously in the last years, which is very good for this community. And but if we really want to understand how feedback works, and we need to look at where the action starts, which is the very central region of AGN. So today I'm going to be focusing on the central 100 to 100 parsecs of AGN of galaxies. So this tiny region here, and this is a very cartoonish view of the different components, let's say, that we can find in the nuclear environment of AGN. So the supermassive black hole, the accretion disk, and then outside the accretion disk, we would have the gas clamps of the broadline region, and beyond the sublimation radius, we would have the dust in the torus, in the equatorial plane, but also in the polar direction, in the direction of the ionization cones. So this is a very schematic view that we presented in this review that Claudio Ricci and I published in 2017. And the message that we tried to transmit with this review was that the torus is not longer the thing that the masterpiece of the unified model, so what produces the type 1, type 2 AGN classification, but also is the ultimate connection between the host galaxy and the supermassive black hole. It's a galaxy structure that is under the sphere of influence of the supermassive black hole. It varies with the periods of nuclear activity, we believe. This material within the torus is much more complex than what we originally thought. It's clumpy, it's highly dynamic, and its properties depend on the accretion properties of the AGN. So certainly much more complex than what we originally thought, which is great because it makes work more exciting in this field. So let's go back now to 10 or 15 years ago. The infrared, of course, is it's the immediate range one thinks about when we want to study the torus, because it's the dusty torus. So the peak of its emission is in the mid-infrared. And we knew from many years now that the torus was very small in the infrared. So the way we had to investigate the torus were either using infrared interferometry, which provided very detailed studies of nearby AGN, the AGN that are more luminous and more nearby. And on the other hand, what we could do was to use images from 8 to 10 meter class telescopes in the near infrared and mid infrared to build SEDs, spectral energy distributions, that we fitted with Torus models to try to understand how the Torus properties vary with AGN properties, with AGN type, AGN luminosity, etc. So the message here, I guess, is that we needed each other, because interferometry gives us the detail that we need for the models to improve and continuously incorporate the features that we see are present in the innermost region of AGN. But then we need AGN samples in order to test these models and look for these trends that I was mentioning. So I said that the infrared is the key range to look at when we want to study the Torus, but not only, because we have also learned quite a lot about the Torus from X-ray observations and submillimeter observations, as I will show. So by putting together all this information in different wavelengths is how we get to have a complete picture of how the Torus looks like. This is another scheme that was published by Sebastian Hönig in his 2019 paper, which precisely tries to combine all this multi-wavelength information about the Torus to try to get a coherent picture and something that we can also compare with the models. So I'm going to show very quickly the different parts that make this scheme. So in the near infrared, we would be observing the hottest dust within the Torus. This is close to the sublimation radius. And this is the kind of study that we can do with gravity. And we will be looking at very, very small scales of radii as small as 0.2 parsecs. Here I'm going to show only the images about NGC 1068, which is only one AGN. But I will talk about larger AGN samples later. Then in the mid-infrared, as Violeta will show in her talk, in the mid-infrared we would have dust in the equatorial plane, but also in the polar direction. This polar dust should be a hollow cone, because otherwise we destroy the unification model, and we couldn't have a direct view of the central engine in type 1 AGN. And this polar component can represent a significant fraction of the mid-infrared emission, even dominating it, but Violeta will tell us more in her talk for sure. And then in the sub-millimeter, we can look at the coolest dust within the Torus, and also at a plethora of sub-millimeter emission lines, which trace the dense gas in the Torus, going from CO to HCN to HCO+. There has been a lot of studies in the last 5 years or so showing how the Torus looks like at these wavelengths. And we found that the bulk of the Torus mass, which can be traced with these molecular tracers, it's in the equatorial plane, okay? So again, the message I'm trying to transmit here is that using all this multi-wavelength information is how we can sort of understand what's going on in the central region of AGN. And like I said, as we provide the people doing theory with new and finer observations, they can improve the models. So we have moved from smooth Torus models to clumpy models. Then they incorporated the polar emission, and now we even have hydrodynamical simulations, hydrodynamical models of the Torus that permit us to understand how the Torus is formed as part of this gas flow cycle. And we can also get predictions for images of different tracers or at different temperatures of how the Torus should look like, okay, that we can compare directly with our observations. And now I'm going to talk about the work that we are doing within this GATOS collaboration. We have published the first 2 papers led by Almudena Alonso Herrero and Santiago Garcia Burillo on volume limited samples of Cipher galaxies very nearby. And Almudena, for example, she focused on the comparison between the mid-infrared and also CO and what we observe in oxygen 3, the ionization cones. And we found that here I'm talking, by the way, about larger scales. So before we were talking about the central parsecs, and here we are talking about scales that go from 100 to 250 parsecs approximately. And what we found is that the mid-infrared emission is still unresolved. So most of the mid-infrared emission is unresolved in the 150 central parsecs. But in 7 out of the 12 cutoff galaxies, we find polar mid-infrared emission on scales larger than 100 parsecs, which is perpendicular to the equatorial plane, so in the direction of the ionization cones. And in the equatorial plane, we see plenty of CO, of molecular gas. In this diagram here, we are representing the Gatos galaxies in terms of Eddington ratio and column density. And also the colors indicate the X-ray luminosity as a proxy for the AGN luminosity. So, and the different symbols indicate whether the mid-infrared emission is unresolved, whether we observe polar dust or equatorial dust or both, okay? And also we are including here predictions from a semi-analytical model by Venanzi and collaborators. And this prediction shows the region of the diagram in which we should expect infrared polar outflow. So the idea is to see whether the polar dust that we are observing on the larger scales of more than 100 parsecs, it's part of these dusty outflows, or is just dust that it's in the narrowing region and heated by the AGN. So this is the kind of thing that we can start to do now with the data and the models that we have, which is great. And something that we notice also from this diagram is all the Gatos with polar mid-infrared emission show higher volumetric luminosity than those without. You can check this in Almudena Alonso Herrero's paper. And this is something that was found also by Omaira González Martín, taking a completely different approach. So doing SED fitting using Spitzer spectra. They isolated the AGN component, and then they fitted with Torus, all the Torus models available in the literature at the time. And so they found that at the highest volumetric luminosities, the SEDs require the Torus plus wind model, so this polar component was more important, whereas at the lower volumetric luminosities, the SEDs could be fitted with clumpy Torus models, okay? So this is one of the aspects that the James Webb is going to cover very well, because at the lowest volumetric luminosities, and these are Ciphers, no mention liners, we do not know if the polar dust is not there or the sensitivity is not enough for detecting it. So this is a clear goal for the James Webb, because we will be able to observe low luminosity AGN and really confirm whether or not this polar dust is present and study the torus in these objects. And also another thing that we can do with the James Webb is precisely to investigate whether this extended polar dust that we see in the mid-infrared, in the case of some objects, at least the most luminous, is part of these dusty winds, or just, like I said, just dust that is sitting in the narrowing region. And this is one of the things that we plan to do as part of the Gatos collaboration with this Cycle 1 proposal led by David Rosario, Leo, and Sebastian Hönig. Then if we move again to the sub-millimeter, when we observe the torus in CO and also in the cold dust using the continuum at 340 gigahertz, in this paper led by Santiago Garcia Burillo, we found larger tori with radii from 10 to 50 parsecs perpendicular to the ionization cone, so in this equatorial plane. And what is great about ALMA is that allows us to study not only the morphology of the cold dust and gas, but also the kinematics. So we are starting to see how the gas is moving within the torus. And for example, we found evidence that the half of the mass in the torus is rotating, and a part of it is outflowing. So this outflow is peeling the outer layers of the torus. And at the rim that the black hole is accreting the molecular gas, the molecular torus can survive for 1 to 4 mega years, which agrees pretty well with the expected lifetime of AGN at this volumetric luminosity. So we see evidence for feedback impacting the molecular gas reservoir in the torus, but also connecting the torus with larger galaxy scales. Here in this image from Imanishi and collaborators, we see that the torus is connected to the CND through molecular gas streamers, which in the work by Santi Garcia Burillo, we interpret it as an outflow of molecular gas that is impacting the CND and producing, in combination with the jets and the winds, this ring-shaped morphology of the CND. The kinematics are very complex. In fact, other authors have found reported evidence for counter-rotation in the torus. So it might be the case that we have two disks counter-rotating among them. So like I said, it's a very complex picture of the torus, much more than what we originally thought. And there is a lot of work to do on this respect. Let me finish by showing this plot also from Santiago Garcia Burillo's work, in which he compared the Nuga galaxy, which are lower luminosity AGN, with the Gatos galaxy, which have a higher volumetric luminosities. And this is a way to measure the concentration of molecular gas in the torus as compared to the CND. So we are talking about 50 parsecs versus 200, okay? And we found that in the case of the Nuga galaxy, so for lower luminosity AGN, the molecular gas is more concentrated in the center. And in the Gatos galaxy, what we believe is happening is that feedback is pushing the molecular gas outwards and producing these lower values that we see here. And in fact, these Gatos galaxies, the higher volumetric luminosity ones, are the ones showing clear evidence for molecular outflow. So it might well be that the more powerful the AGN, the more powerful the outflows, and the larger the impact on the molecular gas reservoir. This has been observed, this redistribution of molecular gas in the inner region has also been found for other Cipher galaxies, for example, for NGC 2110, in this work by David Rosario, in which they see that the jet probably is having it's devoid in the inner region of molecular gas. And we also observed this in a sample of nearby quasars. Here we are talking about somehow larger scales, between 700 parsecs and 1.6 kiloparsecs. But what we are seeing is the action of feedback directly influencing the properties of molecular gas from scales to 10 of parsecs to kiloparsec scale, to the central kiloparsec. So another aspect that we will be able to cover with the James Webb is precisely how is the launching site of these molecular outflows, molecular and also ionized outflows in this nearby AGN, and understand how the torus properties might depend on these molecular outflow properties that we will be able to measure, for example, with MIRI, taking advantage of the large wavelength range. Okay, so in summary, we have a multi-scale and multi-phase torus showing complex kinematics that include rotation, turbulence, non-circular motions. The torus is connected with the host galaxy via inflows, outflows, so it's the innermost part of the AGN feedback process, let's say. And it depends on AGN properties. We believe it's episodic, and it varies in properties quite a lot depending on the wavelength you look at. And we also see this evidence of AGN feedback shaping the nuclear and circumnuclear environment of AGN of different luminosities. And I leave it here with these questions that we'll be able to tackle in the future with the James Webb, but of course with the 30 and 40 meter class telescope that Leo, I'm sure, will be talking about in his talk. But some of the questions are: is this extended polar dust part of the dusty winds that we see on parsec scales? How far they extend? How do the properties depend on the AGN properties and also on the outflow properties? And what is the dust composition of the different parts of the torus? This can also give a lot of and how it's compared with the equatorial dust. And I leave it here. Thank you very much.
Thank you, Cristina. Wonderful overview. So while people are clapping and hopefully thinking about questions that can be posted in the Slack channel or by just raising your hand and I can call you, let me ask you a quick question. You had this this one graph where you showed the and very well in time as well, where you showed the timescales associated to AGN feeding, right? Where you had something like 4 megayears or so for this one particular AGN, 1 to 4 megayears here. So that is still very far away from the flickering timescales of AGNs. Do you think, would you have any hope that we can actually relate the torus properties and the accretion properties at any time, because they are, the timescales are so different? Is there something that you think we can still learn from relating these two?
Well, I think so. I mean, if whether there is even shorter flickering, I guess at the moment we cannot measure that. But at least this time scale, like between, I don't know, 0.1, 4 megayears, these kind of things we can measure. We can start to measure them with ALMA, for example. But variations shorter than that, I'm not sure. No, I mean.
Yeah, that's always the challenge. Okay, I think people are still thinking about questions. Presented so many things, and I see that Robert is typing.
I was very quick. Yeah, maybe I said too much in too short time.
Well, it is a big field. Just a quick second question before while Robert is still typing. Okay, he just wants to comment. Then go ahead, Robert.
Thanks, Leo. Thanks, Cristina. And I thought saying something in person is not faster than typing. So Cristina, thanks very much for a wonderful talk. I was wondering, in the context of the giant telescopes that are coming up, the 30-meter class telescopes, what do you expect for the field of torus research on the nuclear dust that we will be able to do with those great telescopes?
Mm-hmm. Well, you know better than me, So I guess now these very, very detailed studies that we are doing with interferometry of Circino and NGC, I said we because I'm talking as a community, but you guys are doing, we will be able to do it with the 30, 40 meter class telescopes on more AGN, right? So we'll get to see the torus in AGN directly. And compare with the models that we already have and are continuously improving. So we are talking about resolutions of less than 2 parsecs, right? With METIS, for example.
Yeah, thanks very much.
Okay, sorry, I didn't see the hand from Quentin Salome. Please go ahead with your question right now.
Hi, first thanks Cristina for this very nice talk. It was very interesting. My question is about the slide you're showing right now. The ALMA map of NGC 1068. How do you interpret the presence of the molecule over the AGN at the exact position of the AGN? Is it
how it was measured? Sorry, you break up a little bit. So
how
do we measure the position of the AGN, you mean?
No. How do you interpret the fact that you see molecules at the exact position of the AGN?
Uh-huh.
How do you interpret that in your map? Is it real or could it be an artifact from the imaging?
No, this is, so what we see in the center at the position of the AGN is actually the torus, no? That it's, I think I had another image somewhere. So the image that I showed before, it's like the, oops, here. So this is like the enlarged version of this central bit, right? So we observed it with CO221, CO322, HCN, HCO plus.
Okay. Okay, I understand. So on the other image, the large structure, let's say, like the ring you see, it's like
the ring that we see,
a feeding spiral or something.
It's the circumnuclear disk or ring in this case. So it's the CNG, which measures like 200 parsecs in diameter, and it's devoid of molecular gas in the inner region, because the shocks, no, that are produced by the jet and the wind are pushing the molecular gas outwards.
Okay, thanks.
Thank you, Quentin.
We have 2 more questions, and then I think we have to move forward. Ryan and then Walter, can you be quick in your questions, please?
Sure. Yeah, I had a very general question, since I'm not too familiar with this field. But the point in your summary slide about the dust composition of the torus, I was just wondering in general, what does that tell us about the nature of the torus, like whether or not it's small or large grains or silicates or graphite?
So many things. I'll try to be quick. So, for example, one of the things that we can learn with the James Webb is dust mainly in the torus includes silicates and graphites. Okay, so in the very immediate surrounding of the innermost part of the torus, you would expect that maybe only the large graphites survive. So depending on the composition of the dust in the outflowing gas, we will know if this gas comes from the central region, where we only have the larger dust grains, let's say, and if not, it can tell us that it might come from a different part. This is one thing. And also in the models, when you do the models, depending on the size of your particles, the SEDs are going to be quite different. So there are people doing work on this, on trying to modify the dust composition and see how they impact the SEDs.